Here's the answers to the acid-base summative assessment. Some general notes. You would have these questions in any order, but somewhere you had a question asking about which solution was the most acidic or the most basic. The key to this question is to get all of these values in the same unit, whether that's pH, pOH, hydrogen concentration, whatever it might be. But in order to compare these quantities directly, they should all be in the same unit. So I just chose pH. I turned all of them into a pH. The most basic solution would be the one with the highest pH, and the most acidic solution would be the one with the lowest pH. There was a question asking you for a Kb expression. Bases are particles that when in solution remove hydrogen. They're attracted to hydrogen. If you just have a solution of a pure weak base, it's going to take that hydrogen from the water molecules that are present in the solution. That'll always turn the water into hydroxide, indicating a base, and then you'll be left with some kind of a positive ion. That's my conjugate acid. It's positive, acidic, because it's got that extra positive hydrogen. When I set up the Kb expression, I go products over reactants, but we don't include the liquid water. These questions were adorable. They give me 3 acids. Which of the following correctly ranks the 3 monoprotic acids listed from weakest to strongest? These are kind of similar in concept. Weakest acid to strongest acid. And monoprotic just means one hydrogen. So if I look at these molarities, I notice that there's always one solution that's got a really low molarity, 0.023 molar, 0.002 molar. It turns out then that that's the solution that has the lowest pH. Well, the lowest pH must mean that it's got the most hydrogen. And in fact, if you were to go opposite log 0.023, you're going to get 1.6. If you take opposite log 0.002, you will get 2.7. Meaning that in the first example, HX is my strongest acid. And in fact, it is a strong acid. And in the second example, HY is a strong acid. It must fully ionize. So even though the molarity is the smallest, it's giving me the most hydrogen when I see the lowest pH. Now then I've got 2 other solutions that have about the same pH, but yet their molarities are a little bit different. So in the first example, I see the pHs are both approximately 4.2, 4.1, but yet HY had to have a higher concentration in order to produce about the same amount of hydrogen. So in the first example on the left, HY must have been the weakest acid. On the right, it must be HZ. Again, the molarity had to be double from 2 to 4 molar, but yet if the pH was the same, I'm still getting the same amount of hydrogen. But I needed to double the concentration in order to get that amount of hydrogen. So on the right, HZ must have been the weakest, or the one that ionized the least. Now again, feel free to pause at any time as you look through the answer key if you want to check over your math. In these examples, we had a weak monoprotic acid, which we can just call it HX, HY, HZ, HA. And I've been given the pH. We want to know the Ka. And so I think what we forget is that if we know the pH, we know the amount of hydrogen present when this thing is at equilibrium. If the pH is 3, the hydrogen concentration is 10 to the negative third. If the pH is 5, the hydrogen concentration at equilibrium is 10 to the negative fifth. So I set up my ice tables. I've got the initial molarity of the weak acid. I don't care about the water. The acid will be a hydrogen donor, so I'll produce H3O+, and that negative conjugate base. both of those ions will initially start out at 0, but then I can kind of backtrack to figure out the shift. If I know the amount of hydrogen or hydronium at equilibrium, then I know that it went from 0 up to 10 to the negative third or 10 to the negative fifth. My two product ions are both a 1-to-1 ratio, so those should be the same. And then technically at equilibrium, my acid, my HA, would have started at 0.1 molar or 1 molar, and it would have gone down. But that change is so small. And that's why often when we do these ice tables and we're solving for K with weak acids or bases, we kind of ignore that minus X, or in this case it would have been minus 10 to the negative third or minus 10 to the negative fifth. It's pretty small to the point where it's probably insignificant. So from here I've got the two product ion concentrations, and I've got an approximate concentration of my original reactant. It's probably not going to change by much. So it's a fine assumption to subtract that, I should say to ignore that minus 10 to the negative third or 10 to the negative fifth. Now I can plug it in and solve for my Ka. Here we've got a percent ionization. We've got a random weak acid. Same general equation. I've got the percent ionization, and I can use that to determine the Ka. In order to determine the Ka, I somehow need to know the shift. And so I could be given pH, then I know the amount of hydrogen present at equilibrium, or percent ionization is just the percent of the original concentration that ionizes. That's my X value. So that's another way of filling out the ice table. In both situations, I know the original concentration of the weak acid. The two ion products would be 0. And then in the first situation on the left, I'm going to shift it forward by 5% of that 1 molar solution. That's my shift. My reactant, my acid, goes down by 0.05 moles, and my product ions go up. Again, it would be a fine assumption to just ignore that minus 0.05 for my acid. I'm going to put it in there, but with a reasonable amount of sig figs, it's probably not going to change too much. On the right-hand side, I'm shifting forward by 2% of that original, or I should say 1% of the original 2 molar weak acid. Again, that becomes my shift. So you can subtract the 0.02 moles, or again, it's so close to that being 2 on the denominator that it's probably not going to make a big difference. Although I should probably change that. Let's see if I can make it a little smaller here. There we go. There we go, bring it back. That's a 1, right? 1.98. Or you could use 2 and get the same answer. Another ice table. This time we just want to calculate the pH of a weak acid. In order to calculate the pH of a weak acid, we need to be given the Ka. Because now I can set up my general equation. The acid is my hydrogen donor. I'll form hydrogen or hydronium along with the negative conjugate base. I've got the initial concentration of the acid. Initially there are no ions on the product side, but now I know it's going to shift forward and I don't know by how much. But that's when we can call it X. We know X is going to be pretty small. With these being weak acids, their Kas are both very small, less than 1. The second example, it's very, very small, 10 to the negative 10th. So I know it's going to shift forward by not a lot. That X value is going to be pretty small. So I set up my ice table. To solve for X, I can go products over reactants. And here's again where you can just ignore that minus X. It cleans up your math a little bit, makes it a little bit quicker. And with a reasonable amount of sig figs, it's not going to make much of a difference anyways. Once I can solve for X, then I've got the hydrogen concentration of all these particles at equilibrium. In order to calculate the pH, I want to know the concentration of hydrogen or hydronium. So So I'm going to solve for x, and then in either situation, once I get x equals the concentration of hydrogen or hydronium, and then to solve for pH, I can just go opposite log of the hydrogen or hydronium concentration. So in other words, it'll be opposite log of x. Obviously, you'd want to use a calculator for something like this. So again, feel free to pause if you need to double check your math. One of these questions would have been on your assessment. They're talking about sodium fluoride, a compound found in toothpaste, and ammonium nitrate found in fertilizers. When dissolved in water, one compound forms an acidic solution and one forms a basic solution. We want to know the equation that represents the base or the equation that represents the acid. So just double check and see which version of the question did you get. Was it asking for the base or was it asking for the acid? Now they give me some Ka's and Kb's, which is kind of helpful. HA is a weak acid, so fluorine would be its negative conjugate base. The negative ion from a weak acid is definitely a decent base. And it would be attracted to hydrogen. It would remove hydrogen from any water that's present in the solution and not want to let go. That's why HF is a weak acid. So I want an equation that shows that fluorine ion, that negative fluorine ion, being attracted to hydrogen from water to form HF, my weak acid. And what's most responsible for making this a base is the hydroxide. The first choice shows nitrate, which you might think, ooh, nitrate's negative too, and maybe that would be attracted to hydrogen. But they're not giving me a Ka for HNO3, nitric acid. And often if they don't give you a Ka, it means that it's a strong acid. Nitric and hydrochloric are probably the two most common strong acids. In the second situation, when I'm asked for the acidic solution, I'm given a Kb for NH3 ammonia, which means then that NH4, the ammonium ion, is the conjugate acid. So that NH4 could lose its extra hydrogen. It would be picked up by water. And then what makes this an acid? That H3O hydronium. Now again, you've got another option where they've got sodium being attracted to the hydrogen from water, forming H3O plus. But sodium is really just a spectator. Yeah, I get that it's positive, but it's not positive because it can produce any hydrogen. So in that case, it's not going to be acidic or basic. Sodium can't attract hydrogen and it doesn't produce hydrogen. Total spectator, 100% neutral. You would have had a question that looks like this somewhere on your assessment. We've got a table with some Ka's and Kb's for weak acids and weak bases. They were either asking which of the following had the highest pH or which had the lowest pH. So you just have to remember that the lowest pH would be the most acidic, and the highest pH is the least acidic or the most basic. So when I look at my Ka values, in the example on the left, I'm looking for the lowest pH, so the most acidic. I want to focus on the Ka's, specifically the solution that has the highest Ka. 10 to the negative fifth is higher than 10 to the negative eighth. In the second example on the right, when I want the highest pH, I want the highest Kb. I want the one that's the most basic. So I've got two that are a base. They've been giving me Kb's for those two on the bottom. The higher Kb would be the NH3 ammonia, meaning that it's the strongest base. These particle models are really the same question. The choices are just kind of jumbled up. I counted how many particles of each are in the little boxes. We were given HA, just the generic weak acid. A minus would be the conjugate base, and H3O plus would be the hydronium ion. We want to try to identify which of these boxes would best represent HOCl, HOBr, and HOI. So the only difference is the halogen that's going to be bonded to the oxygen. We've got chlorine, bromine, and iodine, which on a periodic table go down the group. I got chlorine, bromine, and iodine. So of these, and I know that chlorine's going to have the highest electronegativity. It's a small atom, so there's more attraction for electrons. And so again, it's kind of like a tug of war. We've got hydrogen bonded to oxygen. So already hydrogen is kind of doomed in that this is a really polar bond. Oxygen has a higher electronegativity than hydrogen. So the electrons are already being pulled away from the hydrogen. But now it's kind of like oxygen brings another pal. And here I've got chlorine with a really high electronegativity. So we're really going to start pulling the electrons away from hydrogen and away from the oxygen even. Up here we've got iodine. It's somewhat electronegative, but it's a bigger atom, so the electronegativity is going to be a lot smaller. So I'm going to notice that in the HOCl, the electrons are always being pulled away from hydrogen. And now I reinforce that by hanging a really electronegative element off the end of the oxygen. And what happens is this bond becomes weaker. If the bond becomes weaker, then it's easier to lose the hydrogen, making it a stronger acid. So in the example on the left, model 1 must be the HOCl, because I don't have as much HA. I don't have as much of the weak acid. There's more ions that have formed, meaning that it's a stronger acid. Whereas the second box must be my HOI, with iodine having the weakest electronegativity, and the electrons are pulled away from hydrogen, but just not quite as strongly. So that hydrogen-oxygen bond is a little bit stronger. Same concept with the example on the right. The boxes are just jumbled around a little bit. Here we were asked to determine how to calculate the pH of a base, specifically a base that produces 2 hydroxide ions. So to some extent this just became a little bit of algebra. When I've got a 0.2 or a 0.1 molar strong base, it's a soluble hydroxide. If it's going to give me 2 hydroxide ions, I'm going to double that concentration. The pOH would be opposite log of the hydroxide concentration. And then I just did a little rearranging algebraically. pH plus pOH equals 14. So then I just took this pOH and substituted it in. Here's my pOH. I'll sub that in. And then just rearrange to solve for the pH. There are a couple questions about the self-ionization of water. So water has a tendency to naturally ionize. We could write it as just a water molecule splitting to form hydrogen and hydroxide. Or in one of the examples here, they showed 2 water molecules that split to form an H3O plus and a hydroxide. Either is totally fine. Now you would have had one of these 3 questions. They all kind of revolve around the same general concept, the self-ionization of water. The top example on the left gives me the Kw at 50 degrees. Now in the packet they give you the Kw at 25 degrees as 10 to the negative 14th. So here at 50 degrees the K is greater, which the Kw is going to be a product of those ion concentrations. It's technically products over reactants, but we don't include the neutral liquid water. So it's really just the product of the hydrogen and hydroxide ion concentrations. If Kw increased at an increase in temperature, it must mean that it's an endothermic process, Because if I increase the temperature, I'm adding energy. If energy is on the reactant side, it's going to shift this thing more forward, increasing the concentration of hydrogen and hydroxide. Now, because hydrogen and hydroxide are always formed at a 1-to-1 ratio, the concentrations will always be the same. I'll always have the same concentration of hydrogen and hydroxide. It's just that it's going to increase a little bit. But pH and pOH will both be the same. They'll be a little bit less than 7 because, again, I'm going to have higher concentrations of hydrogen and hydroxide, but they'll always be the same. Now, the bottom one on the left-hand side says, what if you reduce the temperature? At 10 degrees, the Kw is smaller than 10 to the negative 14th. Well, yeah, because if I remove energy, and this process is endothermic, energy on the reactant side, now I'm going to shift in reverse to replace energy. So I'm going to shift away from the hydrogen and hydroxide. Those concentrations will decrease. Now, in either case, I'm still going to have my Kw, and it's still going to be a product of those ion concentrations. They're just going to be a little lower. Now, to solve for the hydrogen or hydroxide, I can still just take the square root of my Kw. Because again, these guys are going to be the same. So they're going to shift forward. They might be like x and x. So we can say Kw equals x squared. So if I take the square root, I'll get the concentration of hydrogen or hydroxide. And then the last example on the top right gives me the pH of pure water at 50 degrees to be 6.6. Now what's really interesting then is that, okay, if it's 50 degrees, a higher temperature, I'm going to shift it more forward, so I'm going to get more hydrogen and hydroxide. But more hydrogen is going to give me a lower pH. Water will always be neutral. Water is neutral for life, because neutral just means that these concentrations will always be the same. But neutral doesn't always mean that the pH is 7. Water is going to be neutral at 50 degrees, but the pH is going to be 6.6. I'm going to have more hydrogen, but I'm also going to have more hydroxide. So the water will be neutral regardless of the temperature. But the pH of a neutral sample of water won't always be 7. On this one, the correct answer is that it's an endothermic process. If the pH is lower, there must be more hydrogen, so energy must be a reactant. So I'm shifting more forward at an increase in temperature. There's a question that asks you to calculate the percent ionization. To calculate the percent ionization, I need to solve this thing for x. So we've got our weak acid hydrofluoric. I'm going to set up my ice table. I've got a 0.1 molar solution and a 1 molar solution. And I'm going to send this thing forward by x and set up my equation to solve for x. Again, we can ignore this minus x in the denominator, because x is going to be really small. This is a weak acid. So really, to solve for x, all I need to do is cross multiply and take the square root. Now once I get x, that is the amount that's ionized. So percent ionized just is that x value. What percent of the original HF ionized? It's that x value divided by the original molarity, the original amount of HF. So it's kind of like x over the original concentration. Multiply by 100 to make it a percent, and we got it. Now one thing that's kind of interesting too is that if I look at these two side by side, you would have had one of the two. The first concentration is 0.1 and the second is 1 molar. And a common misconception is that if I have a higher concentration, I'll have a higher percent ionization. And it's actually the opposite. They were the same weak acid, but when the concentration was like 10 times higher, my percent ionization was actually lower. But you have to think of this as a ratio. So yeah, X is greater, but I'm dividing by a number in the denominator that's 10 times higher. So my percent, my fraction, ends up being lower. Yeah, X is higher in a higher concentration, but I'm dividing it by a larger number in the denominator. Or if you want to think of this as like a Q versus K, if I call this one K, and here this one is 10 times smaller, but Q is kind of like, this is like 1/10 of K. The concentration is smaller, and so when Q is less than K, we want to increase the amount of product. This is always a ratio of product over reactant. So if I want to increase the amount of product, I'm shifting more forward, which is another way of explaining why the percent ionization is greater when the concentration is lower. Because it's going to shift more forward until Q equals K. Or if you ever had to explain it, we could explain that I'm dividing by a smaller number in the denominator or a larger number in the denominator. You would have had a question that looks like this. They gave you a pH, and we wanted to calculate the hydroxide concentration. In all of these examples, we could take that pH and turn it into a pOH. pH plus pOH equals 14. And then once I have the pOH, the hydroxide concentration is just 10 to the negative pOH. Kind of like if the pH was 9.4, the hydrogen concentration would be 10 to the negative 9.4. You could also use this equation too. Hydrogen times hydroxide equals 10 to the negative 14. Or here I use that equation, pH plus pOH equals 14. I had the pH, I subtracted from 14 to get the pOH, and the third up there as the negative exponent of 10. Now none of the choices look exactly like that, so if you just plug this in your calculator as like 10 caret negative 4.6, then it'll simplify it so that you don't have a decimal in your exponent. And then the last three questions all reference this table. I've got 3 unknown acids, monoprotic, just meaning that they produce one hydrogen ion, and they're at varying concentrations. The first question wanted to know which is likely hydrochloric acid, which is a strong acid. Okay, so I kind of looked at the concentrations versus the pH values and found that, like, for example, if I go opposite log 0.01, I get a pH of 2. Or if I go opposite log of 0.1, I get a pH of 1. And so that HZ, that must have been a strong acid that fully ionized. So that if the concentration was 0.01, I actually did get 0.01 moles of hydrogen. If I were doing the same thing with like HX, if I go opposite log of 0.01, I don't get a pH of 3.44. The pH is a little bit higher, meaning that it did not fully ionize. So both HX and HY must be weak acids. HZ is strong. Now when they ask in the second question which acid had the smallest dissociation constant, now I'm looking for the one that's got the highest pH. You could look at any concentration. HX always has the highest pH, which means that it produced the least amount of hydrogen. That must have been my weakest acid. And the last question wanted to know which particle has the highest concentration in a solution of HX, which we just said was a weak acid. So when weak acids don't fully ionize, the most concentrated particle in the beaker is going to be that weak acid. the amount of hydrogen formed, or the amount of X minus the conjugate base formed, will be much less than the concentration of the original acid.